Great. So today we have actually two visitors here who are interested in, broadly speaking, gauge theories and its interpretation, relation to quantum reference frames, and many other questions and topics around this. And our first speaker today is LUCREZIA RAVERA from Polytechnic University of Turin. And so welcome, it's great to have you here. And we'll hear about the relational bundle geometric formulation of quantum mechanics.
Yeah, thank you. So thank you, Marcus, and hello everyone. It's very nice to be here, to have the opportunity of giving this seminar and to visit this very nice institute. And so today I will talk about a relational bundle geometric formulation of quantum mechanics via the dressing field method, which is based on this work in collaboration with Jordan Francois, that is here too with us. And it will be a formulation of, first of all, classical mechanics, and I will consider M particles classical mechanics. I will provide a bundle geometric formulation of it and then quantize this system. Quantum here will be meant like thinking only of the Schrödinger equation and wave function. And I will show how to make this framework relational. And I will explain this during the talk, but with relational, I mean a relational description of physics of nature is one that captures the physical degrees of freedom in a manifestly invariant and background independent way. Let's say there is no non-dynamical entity in the theory. And this nice interpretation will be possible in this framework by applying the dressing field method, which is a method that is most powerfully applied in a bundle geometric framework. That is why here I will provide a geometric description of classical and quantum mechanics. But it can also be applied at the pure field theoretic level, so with field theoretic degrees of freedom, at different level of abstraction, let's say. And I will explain, so I will also give some technical background on bundle geometry and the dressing field method. It is a method that is constituted, say, by a conditional statement. If you find a dressing field in your theory, which has to be a group valued object and to have some specific properties of transformation. So if you find such an object in your theory, or you manage to construct it somehow from the degrees of freedom that you have in your theory, then you can use it to implement the dressing, that is to make the content of your theory, via this procedure, manifestly automatically gauge invariant, and with a nice relational interpretation. And I will discuss this in the talk. So first of all, let me give you some motivation why to do so. In physics, we have say two main, at least classical scenarios, which are those of general relativistic physics and of gauge field theory. Together we can talk about them and refer to them as general relativistic gauge field theory. And these can be understood in differential geometric terms, typically very well. While quantum mechanics is primarily conceived algebraically. So still, despite this difference of these formulations of these different theories, there is some interest in geometrization of the quantum, say somehow, or anyway in geometric structure underlying and presenting quantum mechanics. For instance, in geometric quantization, this can be just an example. So here I will present you a bundle geometric formulation of, in particular, non-relativistic quantum mechanics. And therefore, in this context, it will rely on a generalization, say an extension of standard bundle geometry, which is called cocyclic bundle geometry, in which essentially, shortly speaking, group representations are replaced by group cocycles. I will show you what I mean with this. And the other peculiarity of this approach is that it is a Lagrangian approach to quantum mechanics. And so it resonates a bit with the historical motivation of Dirac-Feynman that then led to the path integral formulation. And why so? Because this will be a natural environment where to apply the dressing field method of symmetry reduction to achieve the gauge invariant description in this context. And so I will also have a definition of gauge within the structure. And therefore to achieve this geometric relational formulation of quantum mechanics. It will be different from Rovelli relational quantum mechanics structurally, I mean, but its interpretation that I will discuss at the end of the talk resonates also with it, is similar. And it connects with literature of quantum reference frames, as we shall see that the dressing field methods feature transformation of the second kind. And for now, all of this is just jargon, but we will see in detail what I mean with this. That capture the change in a physical reference frame. And so this will make contact with this with this literature on quantum reference frame. And it is mathematically closer, therefore, than to geometric quantization, being a geometric framework for quantum mechanics. So I will first, just as an overview of the talk, I will first of all give you some technical background that will be, first of all, on bundle geometry, to introduce cocyclic bundle geometry, which will be the case for our framework. It will be a cocyclic bundle geometric framework. And then I will tell you the key points of the dressing field method. And and after this technical background, I will provide a bundle geometric formulation of classical mechanics based on these geometric tools. And I will introduce what we call the configuration space-time bundle for n particles that will have a base space that is the Newtonian timeline. I will show how the gauge group in this context, I will define the gauge group in this context, and I will show how this captures extended Galilean transformations. And first of all, I will describe the kinematics, then I will give the dynamics, which will be given by a Lagrangian and action functional. And there we will see that the action functional induces a flat cocyclic connection that I call like this, var pi, not to show that it's flat, it's the RAM derivative is 0, and it's cocyclic covariant derivative. And by means of this, I will show how these capture quantum aspects, how the quantization of this system may emerge within this description by considering the wave function, the quantum mechanical wave function, as objects that are in the kernel of this operator. And we will see splitting. Since we have now the bundle at our disposal, we shall see that if we split now in vertical and horizontal direction, this description, we will get both the prescription for the conjugate momentum, so from the, say, vertical and horizontal projections of this equation, we will get both the prescription for the conjugate momentum and the Schrödinger equation. And I will also mention how these would naturally lead to the path integral formulation. It may arise in a natural way in this context. And after giving this construction, so first of all, I will geometrize this classical and quantum mechanics, and then I will give the relational dressed formulation, so the relational wave function and Schrödinger equation. And I will finally show you how the dressing field method accounts for the freedom of choosing the dressing field, and therefore this will encode covariance under change of physical reference frame, describing the system from within. And then in conclusion, we'll just give you some interpretations, more and more refined statement from what we will get at the classical and quantum level. So let me start with simple standard bundle geometry. So, and I will just mention the key objects to pave the way for the rest of the talk. So we have a manifold that is a principal bundle over a base manifold M, with a structure group H. This is just a schematic graphical representation of it. We have the structure group act on the right of point on the bundle in this way. This defines the right action. And then we have a projection map from the bundle to the base manifold defined in this way. And we have fibers at each point. They are here schematically represented in this way. And they are orbits of the right action of the structure group. So this is just to schematically represent the bundle. Then we may wonder which are the group that are involved in bundle geometric description. And so these are captured by the short exact sequence. Here I'm writing it only to show you which are the key groups that we will be interested in. So we have the group of automorphism, which are those transformations that preserves the vibration structure of the bundle. So those diffeomorphism of the bundle that preserve the fibers. Then we have the group of vertical automorphism that are those automorphisms that induce the identity transformation on M. And these are important because the gauge group, which is the thing that we are interested in under a physical perspective, whose elements I call gamma. They are mapped from P to H that transform in this way. The gauge group is isomorphic to the group of vertical automorphism of the bundle, the isomorphism being given by this. So this is the key group that formally will be interesting in this context, and then I will show how it specifies. All of this is general. Also, the refinement that I will provide on cocyclic bundle geometry are formal and general, and then I will apply them to the specific case of classical and particle mechanics and quantum. Okay. Then we have another other things that are relevant in the bundle that are the forms that we are dealing with and the operators that we have at our disposal. And in particular, the bundle has differential forms and exterior derivative that can act on them. So we have then the group of our bundle can act on differential forms, among which differential form we also find the fields that we deal with. So I will now introduce also them. So we have the right action on forms that is called the equivariance that maps the form and H in this way. And the action via pullback of the group of automorphism on form that I denote in this way. And then gauge transformations on differential forms that are there for this. We have this isomorphism between the vertical automorphism group and the gauge group, and therefore we write gauge transformed forms in this way. And then we have some class of differential forms on the bundle that are remarkable. Why? Because they have some specific properties, some specific transformation property which makes them peculiar. So we have horizontal form that are those forms that are horizontal in the sense that their contraction along a vertical vector field gives 0. We have those forms that are equivariant, meaning that their equivariance is nicely captured by the representation in the bundle. So they have a well-defined equivariance. And then we have tensorial forms, which are both horizontal and equivariant, and these are forms that typically describe the field content of our theory, so they are interesting under a physical perspective. And they gauge transform. This is the gauge transformation rule of this kind of form, and we can see that it is governed by the representation with arguments, the gauge group element. And most importantly, for really achieving the physical degrees of freedom, because this describes fields, but this doesn't automatically mean physical degrees of freedom, invariant degrees of freedom. So those forms relevant in the bundle that are both horizontal and invariant, meaning that, yes, they have their contraction along vertical vector field is 0, so they are horizontal, but they also have trivial equivariance, so they are invariant. Those forms are called basic, and they are important, and they are those kind of forms that are achieved via the dressing field method, those forms that are manifestly invariant. Another relevant point that I would want to mention is the fact that the Durham derivative does not preserve the space of tensorial forms on the bundle. And therefore, we are led to introduce the covariant derivative in terms of here a connection that is a standard Hertzsprung connection, typically like we can see in the description of Yang-Mills theories and so on, thinking of gauge field theory. And in this case, the covariant derivative is useful to preserve the space of tensorial form. It just maps from it from a certain degree tensorial forms to plus one differential degree with respect to the original degree is always tensorial forms. And it gauge transform in this way. So this is the very well-known gauge transformation of the Riemann connection, where gamma is the gauge parameter. Now we can think of all this setup of standard bundle geometric setup and thinking of moving on to the cocyclic bundle geometry. And after having seen the first part on the standard bundle geometric treatment, now we just introduced the notion of cocycle, and once this is done, the rest we shall see it follows. So in cocyclic bundle geometry, the equivariance property of forms and so on, this kind of transformation are ruled by group cocycles. And given a Lie group, we have that a cocycle is a map from P times H, the structure group, to G. And so it's a map of this kind, such that it fulfills the defining property of a cocycle. So essentially, it is given by this formula. And it generalizes representations. Also, as we shall see, it will appear in transformation of forms in the same way as we had the representation before, but now it enters as a group cocycles, and it will have as argument the gauge group element too. So we shall see this now. And this at finite level. Then we may think of linearizing infinitesimal transformation if you want, and therefore linearization of this group cocycle are given in terms of G, so Lie algebra valued objects that I call A. And so we can now think of, so this is more or less, broadly speaking, say the enhancement that we do to describe cocyclic bundle geometry. Now we may look at the group that characterizes this geometric framework and at the forms that we have there. And so the group, they are the same that I was giving before for the standard bundle geometry framework, just extended to the cocyclic one. And what we have is that we have cocyclic equivariant forms that are now forms whose equivariance is given in terms of a cocycle. So this replaces the representation that I was giving before. Yeah. Yeah, absolutely. This is just graphical to representing. Rho was the representation. So now, formally, the cocycle just take the place of the representation in the transformation that I was showing before. Yeah, of the structure group. Yes. Yeah, exactly. It is, it's the group mediating between representation of the structure group and the vector space, if you want, when we map an object on the bundle. In the sense just that it appears now when we think of having forms in this space, so in the cocyclic bundle, we may call it that way, it has to fulfill this property. It takes as entries both the point P and the element of the structure group, H prime, and it has to fulfill this rule. So if we have C that takes as argument P and H prime, so two elements of the structure group, it is defined as to be CPH and CPH H prime. So it has this peculiar structure, the cocycle. We may also see at the end an explicit example of which kind of cocycle you may find in the physics literature. But so what it does is that formally you can see this cocyclic geometry is just taking the forms that we had before and replacing the representation with a cocycle. Yeah. 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 Yeah, no, it's not the same. Yeah, I see. Okay. And so, yes, structurally like this, but then formally what you do is just you replace the representation and you will have as entries always the point of the bundle, the structure group, and then when we move on to seeing how forms gauge transform under the gauge group, the cocycle will have as entries there for the gauge group element. So we have cocyclic equivariant forms, cocyclic tensorial forms that are again both horizontal and equivariant with respect to the cocyclic geometry. And they will gauge transform in this way. Again, I just replaced the representation and I define this for notational convenience. Again, the RAM derivative does not preserve the space of tensorial forms, and therefore I introduce a cocyclic covariant derivative where this var pi is a cocyclic connection, which gauge transforms in this way. This is the defining property of a cocyclic connection. And again, it's like before we had just gamma minus 1, omega gamma, gamma minus 1 d gamma for the Erichman connection. Now, this cocyclic connection gauge transform with the cocycles. So, yeah. Yeah. Yes, well, it depends on the explicit model that one has to consider, because what is given then here formally is just that you have a certain structure group, a vector space, and some group G, and the maps and the cocycle is a group valued cocycle. Then which group is a Lie group with associated Lie algebra, so you have therefore the linearized version of it. But which group is it going to be depends on the model, and so therefore you will have some cocycle which has to fulfill this rule always. But then the grouping which is valued, it depends on the case, on the specific case that you may describe within a cocyclic geometric framework. Yeah, exactly. Yeah. Exactly. Yeah, exactly. Yeah. Yeah, yes, exactly. Yeah. Okay. So this is just formal at the moment, and actually, also when I will specify to the case of n particle classical and quantum mechanics, I will give a more formal description of the explicit treatment. I will not focus on a specific Lagrangian. I can show you then an example of cocyclic of an explicit cocycle for the free case in the paper that I was mentioning before. You can find the explicit example with the cocycle for a theory with interaction terms, so with a non-trivial potential. Here I will be a bit more specific, so the application to this classical mechanics of n particle and the quantum version. And for the cocycle, it will always tend to be abstract. It will be relevant, which is the gauge group element and the gauge group at play in the various contexts, but just that it will be pretty much formal on this side, okay? Because then it's then having clear the formalities, maybe it's then easier to apply it case by case and model by model, depending on the explicit dynamics that we have. So last thing that I want to show you regarding the technical background is the dressing field method. And as I was telling you before, we have to, within the dressing field method, we have this conditional statement that says, if you find a dressing field, then you dress in principle, all the objects that you have into the theory. Therefore, all the forms that I mentioned before, the connection to always all objects that you have to make them gauge invariant. So they are objects that have a functional dependence on object of the bundle. And they are maps from the space of forms on P into the space of dressing field. This is the target group, and this is the structure group associated with the gauge group that is reduced via the dressing operation. And so it's an object that maps maps from P to G, and it has to be group valued and to transform, to gauge transform in this way precisely at the finite level. This is the transformation. For K here, an element of a subgroup of the gauge group. So let me consider what I would call K dressing field, in which we dress only with respect to a subgroup of the gauge group, having in mind that what we would want to do in general in gauge field theory is to fully reduce the symmetry, so to get objects that are fully invariant under the gauge symmetry group. And dressing fields provide bundle coordinatization via physical degrees of freedom. Here we will show this for many particles quantum mechanics. And they are field-dependent objects, typically, so you may also construct them as ad hoc object, introduce them into the theory to have some certain property, some certain transformation property to cure the fact that the degrees of freedom in your theory are not invariant. This is the case, for instance, of H-modes in H-modes literature, and in several other cases. But to have the nice relational interpretation, which the dressing field method provides, you have to extract them somehow from the physical content of your theory. So you check if you have something, or you can build something that transforms in this way and that you can use as a dressing field. And then for a dressing field, we define a dressing map, which again, it's formal, but it's an object defined in this way. It maps from P to a subbundle, P over K subbundle of P quotiented by K subbundle of P. And it is useful because it allows to nicely define for a given form its dressed counterpart in this way via this pullback action. And the dressed forms on the bundle will be naturally belonging to the basic homology of the bundle. It will be kappa basis, so it will be they will be basic forms, and therefore both horizontal and invariant forms. So this is what captures the physical degrees of freedom of any theory. You can apply this to gauge field theory, to general relativistic physics, to general relativistic gauge field theory, at classical and also quantum level. Here we will apply it to classical mechanics to achieve a relational, manifestly invariant, background-independent description of the system from within. And I will show you also in that case which are the dressing fields. This is again formal and very generic to give you the prescription. And always part of the prescription is how to dress field. Once you have found a dressing field, then you have to dress and to make invariant all the content of the degrees of freedom of your theory. And so you take, for instance, the dressing of an Hershman connection, and of standard tensorial form is given. This with omega u and alpha u, I denote the dressed object. For cocyclic connection and for cocyclic tensorial form, this is the dressed version. As you can see, how do I build those dressed objects? I just apply a rule of thumb of the dressing field method, and you can check it explicitly that it's just that it works. That is the fact that if I have some forms and I found the dressing field, to compute the gauge, I just compute the gauge transformation of the forms. And so I start from the original I gave you before on the technical background on standard bundle geometry and cocyclic bundle geometry, the gauge transformation of these objects. And then I just substitute formally the gauge parameter with U, the dress field, to get the dressed invariant K basic, in this case, form. Despite this formal similarity between maybe dressing gauge fixing or anyway gauge transformation, note that the dressing field is not an element of the gauge group. So dress fields are not gauge fixing or gauge transformed version. And also gauge fixing is never invariant, while dress forms are. And this is, for instance, nicely described in a paper by Philip Berghofer and Jordan. but you may also find this discussion in several recent works of us in which we explain this at different levels, also more abstract field theoretic descriptions in bundle geometry of field space. It is nice the way in which you can understand these differences. So for now, just know that there are different operations. Then we can talk about this also later at the end of the talk, why they are different, what they differ more explicitly. And so dressing fields, as I was saying before, they depend on the dynamical degrees of freedom in such a way that dress forms have a nice relational interpretation, and in the sense that they encode the gauge invariant physical relational network of degrees of freedom among the dynamical degrees of freedom of a theory. This was first noticed in our work in collaboration with John, and now in several works that we did together. Yes? Sorry, I didn't get the beginning of the question only. So if it is, yeah. Okay. All the gauge invariant form, I would say, these are, I don't have a definite reply to this, but I would say all those gauge invariant forms that also have a relational interpretation, because suppose there is some way to achieve gauge invariance, but with a background dependent method, I don't know, something like that, but truly gauge invariance, so not like in a gauge fixing, in which you can still transform the gauge slice. But suppose you get this, you achieve somehow gauge invariance, still you have to see if you have this nice relational interpretation. And you may also think, for instance, of a perfect gauge fixing in which you just have fully gauge fixed the slice, somehow also reduce the residual gauge transformation and so on. Still, a gauge fixing is a map from is a section of the bundle, while dressing allows to achieve the basic cohomology. So for instance, in field space, it will allow to achieve a space that is isomorphic to the moduli space. So it's different. I wouldn't say that there is, I mean, all dressed objects are gauge invariant, but vice versa might be delicate depending on the interpretation that you give to these gauge invariant objects. Okay, sure. Okay. So I introduced a K dressing field, so where K was a subgroup of the structure group, and Matt called K a subgroup of the full gauge group, because I wanted to mention residual transformation of the first kind within the dressing field method, that are those transformations under which the dress form still transform when you have therefore some part, some subgroup of the gauge group that is not fully reduced. So you still have objects that still gauge transform. You have just partially reduced your gauge symmetry. And those are meaningful in the case in which you have a normal subgroup. K is a normal subgroup of the structure group. And therefore the quotient HK is a group. And you can define nicely J variable, the dressed fields as J variable transforming under J transformation. And to find the gauge transformation of the dressed object, you already know those of the bare fields, say, of the bare forms beta under J. So you just check how the dressing transform under those, and you get the J gauge transformation of the composite object. Most importantly, so this kind of symmetry is something that you want to get rid of in principle, unless in particular set up, as it will be the case in this talk, but because we are providing a geometric description of something that naturally is not. So here we are constructing something that is slightly different, but in standard gauge field theory, you would want to make, to achieve the gauge invariant description under the full gauge group. And so you may have those, but then you still reduce the symmetry, finding another dressing and so on. It can be done step by step. But then there are also transformations of the second kind. Those we named at the beginning when we introduced them, we named a residual transformation of the second kind. But then we decided to rename them as transformations of the second kind to avoid confusion with residual gauge transformations. Those have nothing to do with those. They are transformations typical in the dressing field method. And they are transformation of the dressed object that arise from a possible ambiguity that is typically there in the choice of dressing field. And for instance, you may have two dressing fields bringing the relational invariant description of your system. They are related by a group element in this way. They transform into each other in this way. And in simplest cases, they don't act on bare objects, on the dressed form transform in this way under this transformation. And in particular, you can also do that for cocyclic dressing field that therefore have to gauge transform with a cocycle, and they will be related by these symmetries in this way. And therefore also for cocyclic form that we will be interested on, they would transform in this way. And they are important, as we will see explicitly, because they capture frame, so there is not something that we want to reduce, because it captures some physical law, something important. It's telling us something physically important of our system. So the fact that we have a frame change covariance of the geometric relational quantum mechanical description that I will provide. That is something that we would expect. It's kind of a democratic access to the fact of being a physical reference system of each subsystem of our original system, okay? So now this was the part on the technical background. I would want to show you the classical mechanics framework within this geometric setup and then quantize it first of all. So as I was mentioning before, I introduced what I call a configuration space-time bundle over the Newtonian timeline, in which each point of the bundle, P, corresponds to the instantaneous configuration of n particles and classical particles at this stage. And the structure group is R3n, so R3n times. We can write the right action of the structure group on the configuration space-time bundle, and then all the technicalities and the formal aspect that we have seen before we can now apply to this bundle structure, and it will be a cocyclic bundle structure, as we shall see. So we have this right action of H is additive abelian. Each form is transformed by a quantity X. And it can, in principle, each particle is shifted by a different vector xi. And if we consider this setup, then any configuration of particle, on the other hand, is left invariant by a subgroup of this structure group, and I call it the diagonal subgroup with this delta here, which correspond to having all the particles in the same configuration shifted by the same amount, by the same shift. And so we can see that under this perspective, since this H delta, so this diagonal group is a normal subgroup of H, then we have the quotient H over H delta is an abelian group, and we can decompose H in this way into two pieces related by semi-direct product. We have H internal and H external. H internal implements physical changes in the configuration of particles as seen by each particle within the system itself, so different changes. While H external, so, which is related to this diagonal part, only reflects a global change of the whole configuration, and it corresponds to something that can be seen from the outside as the view of an external observer just seeing all the configuration shifted of the same amount. And so that's a way to understand why this configuration space-time bundle has a double fibration structure. We have a first fiber that is H external, and if we look at if we think also more of reducing the symmetry, we are led to C relational, and I will show you how to access this bundle geometric description after via the dressing field method. But then it's still fibered, this space, with respect to the structure group H internal. And so what we would want this project then via pi 2 into the Newtonian timeline, and what I would want to achieve So first I will give you the classical description, then the quantum, and then the relational classical and quantum description. I would want to achieve something that is isomorphic to this space, that captures, that represents, say, this space, which is the relational configuration space-time bundle, where the internal relative dynamics occur. Again, so yeah. It can be, yeah, I will describe this now. Yes, it's true. It depends on T, and it will capture several transformation. In the most general case, extending Galilean transformations. But yes, absolutely, yeah. And yeah, but it's of the same shift all the system in that case. While in the other, point by point, you can have different shifts which correspond to different internal dynamics. Indeed, yeah. Okay, yeah. Yeah, you are shifting, yeah, I see what you mean. You are shifting all the points in the bundle of the same amount. So, and then these project, so this is a first vibration, like external observer description of the change of all the particles of a certain amount, constant even amount. And then you have H internal, which are those transformations that will be actually the physical one, and those projected to the Newtonian timeline. Okay. Okay. And so each point of the boundary itself represents all the configuration, the instantaneous configuration, so depending on T at a certain instant of all the particles in the set. So, as we have seen before, we have introduced the group of a bundle, so associated with a bundle geometric structure. Here also we can see which are the relevant group associated with the configuration space-time bundle. So again, we have the group of automorphism, which induces are those diffeomorphisms of the bundle that induce diffeomorphisms of the timeline. The group of vertical automorphism, which induce the identity transformation on the Newtonian timeline. And then we have the gauge group that is isomorphic to the group of vertical automorphism. And it acts simply so if we write the right action in this way, they are mapped from the configuration space-time bundle to the structure group, and I call them in this way, capital X. And it includes the Galilean boost, the gauge group H, which is the case in which indeed the gauge group element depends on T, but with something that is constant. We have a constant factor, which is V external. And this is an element of H external, is a constant, is the relative velocity between the configuration P of the n particles and the external observer. So constant objects time T. But on the other hand, more generally, H encodes extended Galilean transformation, so an X that depends on P in this way. And then we can write it explicitly also in bundle coordinates. And they transform in this way. Elements of the gauge group are basic, and so the element of H actually depend only on the Newtonian timeline, as you were also noticing before, on elements of the Newtonian timeline. In the same way in which we have decomposed before the structure group into external and internal parts, we can do the same now for the group of automorphism, of vertical automorphism, and therefore for the gauge group we have this structure. Yeah. Is the configuration of all the n particle, maybe like this. Okay, no, sorry, it's here. It's P1, Pn, I call it P, so the instantaneous configuration of the n particle. They can get shifted in principle of different amount, and in the case in which the same, the shift is the same and can be written as a Galilean boost is H external, okay? Yeah. Exactly, yes, exactly. Okay, so we split also the gauge group into internal and external. And then we can define a cocyclic geometry on the space-time configuration bundle via cocycles. Again, this G depends on the model that we will analyze explicitly on the model given I will show you in a while. And then you know that you have these objects now that are cocycle that have to transform, that fulfill this property of cocycle. They take as entry a point P on the configuration space-time bundle, which represent the configuration of the n particle. And these arguments, it takes also as argument the element x and x prime in this case, because this is its defining property. And then we can write, once we have introduced this cocycle, we can also write the corresponding linear one cocycle, which I call A, is the linearized version of the cocycle. And then we can take forms on the bundle, and they will be cocyclic tensorial, cocyclic equivariant. Here, for instance, this is a cocyclic connection. And they will gauge transform via the cocycle, which will take as explicit entries now the gauge group element of the gauge group that we are now considering the split in this way. Okay, so these are the kinematical level. And then we would want to study some dynamics of the theory that might be a free theory and interacting theory in more realistic cases. And so the dynamics will be given for the configuration of n classical particles will be given by a Lagrange that is one form, a cocyclic one form, a cocyclic tensorial one form in particular. I call tiny c here the cocycle, and because x exponential will be capital C, the group element, the group cocycle, and we will see this in a while. So how can we see this? We take its gauge transformation of the Lagrangian, and you can see that in general it transforms with a cocyclic object. This is you can find also in some textbook this kind of property. If you see the typical for a system of n free particles, this is an example that we can also see explicitly after, the boundary terms by means of which the Lagrangian transform for free particles, free n particles, it's a group cocycle. If you check its defining property, you apply this formula, you will see that it fulfills precisely this formula. Then you may consider at the linear level, so at the level of the Lie algebra associated with the gauge group, what happens. So consider the infinitesimal transformation of the Lagrangian. And the infinitesimal cocycle, I will show you this a bit more explicitly now, why it encodes the Euler Lagrange equation of the theory. And then now we can do two main things with this Lagrange. We can, in principle, take a local section on the bundle that represent a trajectory of history. And we can take the local representative of the Lagrangian on the Newtonian Thalami in bundle coordinates, which is just given by the pullback along this section of the Lagrangian. If we do so, we get this description, which is, this is a kind of Lagrangian density integrated, to be integrated in dt to write the action, but anyway, is this expression, which we are familiar with in physics, is the typical way of seeing formally a Lagrangian in field theory. On the other hand, we can now also take a curve from an interval I in R to the configuration space-time bundle, and therefore it maps the parameter tau into gamma tau, is therefore parametrized, we say, in this way. We can define the tangent vector field in this way, where with the dot symbol I denote object derived with respect to tau. And then I can consider the restriction of the Lagrangian on this curve gamma, so it's pulled back to the interval I. And I will call it a small l in this way, is the pullback of the Lagrangian. And if we do so, we get this expression, which involves the parameter tau. And so these are two descriptions of the would be then same theory. Just one is what we call the unparametrized form, and this is the one that we are used to when we do classical mechanics. While this is the parametrized version, and we can also see that for t dot equal 1, so for a particular choice of t dot 2, are easily related. If we now take x dot written in this way in terms of dx dt t dot, so x prime t dot, we can see that x prime is the physical, so the measurable velocity of x of the particle, so it's just defined in this way in terms of t dot. And then we can, once we have these two description, we can now look, in particular, we are interested in this one, and I will show you in a while why so. But we can now take, as we did take the gauge transformation before of the Lagrangian, we can now take the gauge transformation of L gamma, because we have that the curve itself transform under a gauge group element, so we can write the transformation of this tiny L, and we get again that it transforms with a cocycle that I denote in this way. It's, yeah. Exactly. Yes, absolutely. Yes. A total derivative term that if you check its properties, its entry will correspond to the defining property of a cocycle. That's precisely the point. It's gauge variant because it transforms in that way. Gauge invariant would be that this term somehow is cancelled by means of the way in which you implement this reduction of the gauge symmetry. And exactly, yes, and the gauge symmetry in this case is even more peculiar because usually gauge symmetry, we say, is not physical, it's a redundancy of the theory. It gives us some principle for writing, some symmetry principle for writing the Lagrangian, but then we require gauge invariance, and so we would want to achieve a gauge invariance of the treatment of our description. In this case, the gauge group for the way in which we treat geometrically this kind of system, these mechanics, the gauge group element is a part that is the external part, so all shifted, all particles shifted of the same amount, that is non-physical, and this is the one that I would want to reduce indeed. But the internal part, it represents a kind of physical transformation, different shifts. So that part, you may try to reduce it, you may, but actually you would just want to see how those dressed objects, they transform under that symmetry, but it will be, yeah, just that. So it will be invariance under the gauge transformation associated with the cocycle that is indeed a boundary term, okay? Okay, let me see if I can speed it up a bit here, okay? This is just the way in which we can relate x dot, so the gauge group element, to the physical velocity shift induced by extending a linear transformation. So from the geometric formalism, then you can derive more and more subtleties within the framework. So let me just try to capture which are the key objects to give you then the results. So we want to write the dynamics of the theory by means of an action. It will be an action that is given by the integral of the Lagrangian over the curve gamma. And so we can write this integral as the integral over the interval I, and we pull back the Lagrangian to be able to integrate over the integral. So we pull back along gamma. And we get exactly this description of the integral. So with, as I was mentioning before, setting t dot equal 1, we will move to the unparameterized version. And then again, we look at how the object gauge transforms. And so from the gauge transformation property of the object that I described before, we get those of the action, and we see that it transforms with a cocycle. It's a linearized version. And then we may think now of defining the classical dynamics as the critical points, in this case, a critical curve of S, and I will call them gamma critical in this way, such that they are on shell, such that the description is on shell. So the Euler-Lagrange equations are fulfilled. And this is treated in more details in the paper on which this talk is based. But if you now look at how we can write this field equation in a formal way, you can derive them from the vanishing of A, chi, in this way. So from the linearized version of the cocycle for a general variation of the Lagrangian. If you're interested, you can also see this in details in the paper. So you just want the classical dynamics, and so you define as at the critical points of S, critical curves. in this way, by looking at this structure for gamma equal to gamma critical, you have that this object is the Hamiltonian, so S gamma critical will be the Hamiltonian principal function. And in fact, you can prove now that it satisfies the Hamilton-Jacobi equation, which are those, where H is the Hamiltonian as a function of x, pi, and t, and pi gives us the still classical at this stage, but the prescription for the canonical conjugate momenta, so that is ds along gamma critical dx, and it is the conserved and other charges. So this is just in this classical description. But now we may look, we have this cocyclic geometry underlying our description. And so we can notice that if we define this cocycle as the exponential of the tiny c that I introduced before, then the action induces on the space-time bundle, on this configuration space-time bundle, a flat cocyclic connection, because if we now take this expression as defining our flat cocyclic connection as ds, it is therefore automatically flat, its derivative is 0. And it is cocyclic, which is inherited from the transformation property, from the cocyclic transformation of the action itself. So we can, this is key, if we have to remember something till now, a part of the technical background, but this is key, the fact that we introduce an object that is defined as ds, and it is a flat cocyclic connection precisely because of the geometric properties of our construction and the gauge transformations of our construction. And then for gamma critical, we can do this split along dx and dt, and have, again, a nice prescription for the conjugate momenta in terms of contraction along vertical vector fields of this flat cocyclic connection. Now, and the easiest object, a simple object that we may introduce in our framework is a cocyclic tensorial zero form. Let me call it psi gamma, meaning that it's just an object that is tensorial, a zero form that is tensorial and is cocyclic tensorial. Therefore, it transforms, as I was mentioning before, with the cocycle. And we can now introduce, as once we have the cocycle and forms and the RAM derivative d, we can introduce, we would want these spaces of this kind of forms to be preserved. And therefore, we introduce a cocyclic covariant derivative, which preserve, therefore, cocyclic tensoriality. And we introduce, therefore, this covariant derivative of this psi object in which the cocyclic connection appears. And now we can say that, at least formally, but we will see now what happens more explicitly, that the quantum mechanical statements are encoded in the fact that psi evaluated at gamma critical is in the kernel of this covariant derivative operator. This defines the space of the wave function. So the objects that are in the kernel of this cocyclic covariant derivative. And also we have then a prescription via cocycle again of how to move from gamma critical to any gamma. And so we call wave functions the object that fulfill this equation. And why so? Why we say that quantum mechanical is kind of captured by this statement? Because if we have the bundle geometry, the cocyclic bundle geometry at our disposal, and so we can take this equation and split it, analyze it along vertical and horizontal directions, so along dx and dt. And by analyzing it along dx, we get the kinematical actions, say, of quantum mechanics. So from the horizontality property of this equation, we get, we plug back into this equation this with its definition and we analyze it along dx, we get the prescription for the momentum operator in terms of ddx. And if we analyze it along dt, we get the dynamical axiom of quantum mechanics, that is the Schrödinger equation. Therefore, the derivative in time of psi equal to h psi. So this is the reason why I would call those objects that are in the kernel of this operation wave function, because if I analyze them in bundle geometric terms, I get the prescription for quantum mechanics. And also, we may notice at this stage that we may now think of taking solutions of this equation. They are object of this form, but we know that bar pi was related to S, so we may write them in this way, and this is the prescription for the Dirac-Feynman path integral formulation within this setup. This is the correlator, so we can write it in this way as an integral over a domain between 0 and 1 along the gamma, along all possible paths or possible histories of psi gamma in this way. Given all of this, now we would want to, so we have this geometric setup, we have a physical description, classical and quantum of our theory, we would now want to achieve its relational description, and therefore apply the dressing field method, both at the classical and at the quantum. Therefore, you see that with this geometric treatment, it kind of follows in a natural way, and so we can just apply the dressing field method and see what happens. The point is to find a dressing field. And what happens is that we want to achieve something that we want to realize the relational configuration space-time bundle. We are the dressing field method, reducing the external gauge group that I was defining before. So we would want the dressing field method to be well defined as such. So we would want it to be a map from the configuration space-time bundle to H external, and to transform in this way. This is an additive abelian simple case, so it has to transform in this way to be a dressing field in such a way to define a dress map in this way that allows whose image will be precisely the subbundle of the configuration space-time bundle isomorphic to C relational via dressing. Therefore, I denote it formally in this way. So how can we produce such a dressing? We look at the degrees of freedom that we have in our theory. We have particles, and in particular, we have the position of each particle. And so we notice that if we take as a dressing, say, ith dressing here, ui, depending on the point on the bundle, if we define it as minus xi, so n times for all the particles in each configuration, we can see that it properly transforms as a dressing field. So the position of each particle within our system can be considered as a dressing field for this kind of systems to implement a dressing operation. And via the dressing map associated with the dressing, we can see what it means. It means that each point is therefore shifted by xi in this case, so we can write the dressing map. This is just a feature of the dressing map, but most importantly is the fact that if we have picked, say, the ith particle, the position of the ith particle in our system, it will rest, it will stay in its own frame, so the zero of this coordinate choice for it will correspond to the zeros in the coordinate, in the position. It will be in its position 0. In other words, ui, so the dressing, outputs the position of the ith particle of the configuration, and the image of the dressing map is the realization of the relational configuration space-time bundle from the viewpoint of the ith particle. So it's a description from within the system. This is schematically represented in this way. And then we have, as I was mentioning before, residual transformation of the first kind, because we know that we had the gauge group that was split into external and internal part. We have reduced the external part, so we still have gauge transformation under the residual part of the gauge group, that is the internal one. And the structure group, therefore, is this. We may write these elements in this way, y minus yi is the shift corresponding to the fact that we have chosen a dressing field within our theory. It is isomorphic to H internal, and so we may write easily in this way. This is the formal piece that will appear, and you can see this explicitly also in the paper. It's the residual gauge transformation associated with our system. They are the physical transformations, so we wouldn't want to reduce them in principle. But most importantly, we have transformation of the second kind, which captures physical reference frame covariance of the relational description. Because now we may think of having another dressing field, and in fact we have it. It's just choosing another particle within our pool to describe the system from within. And it will give us another configuration, another realization of the relational configuration space-time bundle. So I denote this uj, and the previous was ui. They are isomorphic. And the two dressing fields are related by Zij, which parameterizes the multiple realization of this relational bundle. And essentially, it allows to switch between internal relational viewpoints. So we can see this again well with the dressing map. If we take FU I, so the one that I introduced previously, here is the fact that we are in the zeros of the X position. And this is the way in which we can introduce these gauge group elements, the Zij, capturing this shift of the fact that we have selective a particle as a reference system. If I now write the dress map for Fuj, I look at the various entries in the position for the different particles. I see that the 0 now is in the jth position, and Zij is the way in which I translate Ui with respect to Uj. So it's Fuj plus Z Ij. And so also, now that we have found, as I was mentioning before, again, when we find a dressing field, or many of them are related by transformation of the second kind, then we would want to dress all the content of our theory to make it relational, and therefore not only to be gauge invariant, but also to analyze what it means to have this relational description from within in this particular system. We will see this at the end of the talk. So we dress the curve. So this gamma u will be the relational history of an nth particle configuration from the viewpoint of any particle itself. And then we dress the Lagrangian one form. Again, we apply just simply the dressing field method rule of thumb. We look at the way in which the object transforms under gauge transformation. We formally replace the gauge parameter, in this case the cocycle that has as entry the gauge parameter, with the dressing field, and we get the invariant object. The Lagrangian, the dressed Lagrangian will be like this. It will be basic under H external by construction, and therefore H external invariant, so invariant under external gauge transformations. And the transformation of the second kind for the Lagrangian will, under the perspective of the Lagrangian, will capture how the Lagrangian description is changed when we shift to distinct particles in the same configuration. So it's a discrete change in this case. In most relevant cases, these transformation of the second kind are discrete, and they really show a change of a reference, okay? Then we can do the same for the dress parameterized Lagrangian. We get this expression, which is the relational Lagrangian from the internal viewpoint of another particle in the same physical history. Then the dress action, same way, and this capture, therefore, the classical relational dynamics. So we can think of varying then the relational action and getting a relational variational principle. Same for the cocyclic connection. We dress it by using the dressing field method rule of thumb. It will be subject to transformation of the second kind, and it will be written in terms of the dressed action, and it is again what will allow then to move on to the quantum mechanical description, to dress there and to get a relational quantum mechanical description of our system. And indeed, now we apply the dressing field method rule of thumb of on the cocyclic zero form that was then described in the wave function. We get this expression, and if we now introduce the cocyclic covariant derivative, then we dress also the cocyclic covariant derivative, meaning that it will have, if we apply it to psi dressed, it will be the derivative of psi dressed plus the dressed cocyclic covariant derivative times psi dressed. So everything is now dressed, everything is relational, and we have to just finish the interpretation of what we got. And so we obtain the geometric relational quantum mechanics, which is encoded in the statement that the space of dressed relational wave functions is described by the object in the kernel of the dressed cocyclic covariant derivative. And now, if we split, if we decompose this equation along the x, dress, and dt, we get the relational version of the momentum operator and the dress, the Schrödinger equation, naturally written in terms of invariant object. And again, in the same way as before, it was natural then to construct the path integral to move on to see as arising, say, the path integral formulation. Here we will have the relational path integral, the dressed path integral formulation for both dressed objects, for both dressed curves and dressed entries. So this means that somehow, yes?
So these dressed x's, I can understand them as x2 minus x1, x3 minus x1.
Yeah, exactly. Yeah, we had the dressing map.
For the dressed pi.
Pi for the rest, yes, I mean, with respect, as you mean the momentum, as defined with by means of the derivative with respect to the dressed x. So yes, there is always this kind of shift encoded. The dressing in this case, being an abelian.
P2 minus P1, P3 minus P1.
I'm not sure about this, how it will be, because it will mix, yeah, I think it's not like x minus x, it's not the same functional dependence, if you mean. But it's written in terms of objects that have this rule, say, this description in the operator.
Because the physical interpretation of the x is very simple. I just measure the
Exactly.
relatives to me, but the
Absolutely.
pi is not that I'm measuring
Yeah.
relative velocities with respect to
Exactly.
I will have to do something extra.
Yeah, exactly. Yes, yes, I would agree. Yeah. Yeah, the easiest thing, now I will try to provide you also with an interpretation of these results, meaning what does it mean to have relational history, so seen from within. What does it mean to have a relational wave function, a relational state? So I will provide interpretation. But the easiest one that we can see is the fact that since the dressing is given by x, by the position of a particle, each particle acts as a dressing, by means of its position, and so there is really this combination of x minus something, till we arrive at the x of the selected particle as addressing itself that we rest in its own frame. I mean, we rest its xi minus xi, say, so it will be 0 in it's the origin of the coordinate system. So another, this is just to conclude, another aspect that is key into transformation of the second kind is that if we now just take a look at the form in which we can write them, so this is for dressing field, how they are related by transformation of the second kind. Now we can look at how the relational wave functions are related by means of this transformation of the second kind. They are forms dressed cocyclic tensorial zero forms. So now they are dressed objects. They are invariant on the two representations, say, of the configuration space-time bundle. So dressed with respect to ui and uj. If we look at them in bundle coordinate, they are written in this way, where we can see precisely this property that we were mentioning now. And if we look at the way in which they are related to each other, so the xi and xj dressed are related by this cocycle, we take as entry now zij. And so this is nice because change of physical reference frame is, we can see that it's a unitary transformation of the relational quantum state of the relational wave function. And it is implemented by u-valued one cocycle, in fact, that takes as entry precisely this zij, this z element. So to conclude, let's see how we can interpret this framework. So there is a first way, a first reading of the key results that we have seen in this geometric relational quantum mechanical framework. And it's the fact that if we consider a reference subsystem as, in this case, a particle within our pool, it sees itself as classical. So there's no strong argument here for a quantum reference frame if we think only of the particle itself as quantum. The particle itself is classical. The quantum description arises in the moment in which we put it in relation to the other entries, to the other object in our subsystems, in this case, the n-1 particles in the n-particle configuration. And these are described quantum mechanically under this perspective. It's there that we have the quantum mechanical wave function, path, and path integral, and so on, the description that emerge at that level. Yet, we have those residual transformation, or better, sorry, transformation of the second kind that implement physical reference frame covariance. And these, as I was mentioning at the very beginning of the talk, ensure kind of a quantum democracy, we may say. So the fact that any subsystem is as legitimate as any other in the system to act, to witness the quantum dynamics created by the relational network. Therefore, when this is a first reading, then we can even refine this interpretation with a refined and more accurate, say, understanding, is the fact that there is no meaningful way for a given reference subsystem, in this case a particle, to assign itself a relational quantum state. It's only so with respect to the others, in interaction, in presence of the others, and so it can do so only for other subsystems which are assigned a wave function with respect to the particle itself. So this is the interpretation of the Dresde invariant and relational wave function. And we can still say it otherwise, so it's the fact that if we take a subsystem, a particle, in this case, it only makes sense to assign a quantum state actually to the set of relations, to the relational network between itself and the rest of the world, the rest of the system that we have at our disposal. And within this framework, the physical reference frame covariance implemented by G transformation, by transformation of the second kind, ensures that we have the equivalence of any subsystem in the system itself to act as a viewpoint, to describe from its viewpoint the collective relational quantum dynamics. And that's also, thank you for your attention.
Thank you very much for the nice talk. Are there questions? Manuel?
Yeah, thanks a lot. I'm very interested a bit in this interpretation for the cocyclic formulation, because I've never really heard of this so much. I mean, cocycles a little bit, but then viewing it as a kind of generalization of the representation part, yep. I'm very interested if perhaps there is any kind of physical interpretation of what that could mean in some example. Yep. I'm assuming that perhaps internally nothing would change in some sense, but perhaps like externally there would be a difference to some external observer, whether you are in this cocyclic framework or just in a representation framework. So I've no intuition about it, but if you have, I would be glad to hear.
Okay, yeah, thank you for your question. And yeah, sure, I can show, I have some backup slide. Well, let me try to, okay, this is an example. First of all, say, yeah, cocycle generalizes representation, and cocyclic boundary geometry, it seems somehow relatively new in mathematics, I would say. Maybe not that much, surely in physics, but it actually underpins somehow a lot of the Lagrangians that we have in gauge field theory and general relativistic gauge field theory, because they are objects that transform with that kind of object that we may see truly as a cocycle, as a group cocycle. Then what happens is that when we do model building, when we study some model, we see just maybe the object that we get under some gauge transformation, external, internal in this case, or anyway, a gauge transformation, and we just then deal with it, try to make it gauge invariance. There might be different technique, different gauge fixing technique. But then if we analyze the object itself and the geometric group theoretic structure that we have underlying the theory, we discover it is a cocycle. So it's a formal way to describe this object. And in fact, this is an example if we restrict, for instance, our treatment to free particles, so a Lagrangian free particles, and we know which would be its standard description with t dot somehow equal 1. So, but here we make it a bit more complicated just to see which is the geometric structure of the theory. So it will be described, this is the pullback along gamma, so it will be described in this way, x, t, m, the mass. So this is just a free theory. And then the unparameterized version that we get is this, setting t dot equal 1. And if we look now at this Lagrange, but if you want at capital L, but also the cocyclic properties reflecting on the tiny l, we can see that it really transforms as a cocycle. And the structure of the cocycle is this. X are the element of the gauge group. So this is the explicit structure of the cocycle. And we have those in general, we may see them as extended Galilean transformation, and we would get the Galilean boost in the case in which just x is equal to vt. And this is a nice example because we can see something that we are pretty confident with, that we recognize from the literature, from textbook. And this, the Lagrangian is not invariant under Galilean boost, it's quasi-invariant, it transforms with a boundary term. And indeed, this, we write it formally, with this pairing with this product that we have introduced here to describe them, but the point is that you get an object that is a boundary term written in this way, and therefore it is sometimes denoted as delta in the literature, and it is precisely the cocycle, but it's just this boundary term written in terms of v and x in this way. So it depends, that's why I was saying it depends model by model, group by group, which is the group involved. In this case, we can see a simple example of a cocycle, but for instance, and so of course then all the rest of the treatment of the theory follows, just following the formal aspects that I showed you before. But what you may see is also, for instance, in gauge field theory. If you take, I don't know, Chern-Simon theory, you look how the Lagrangian, so non-abelian Chern-Simon theory in 3 dimensions, you look how the theory transform. You write the transformation of the Lagrangian. At the finite level, you will see that it transforms with a cocycle, and it's not only a boundary term. At the finite group level, say, at the finite level, it's at boundary terms plus a further piece. And only if you look at the linearized version, the infinitesimal version, you will see that this boils down to a boundary term. So, but that's a cocyclic. It transforms with a cocycle, even though usually we just compute the gauge transformation, right? What it is. Okay.
Thank you so much.
Okay, sure.
Let me ask a question about. Yes. So about the dressing fields. So I understand that in the case of n particles that you've shown us, you could say if I take the ith particle, then I get a dressing field, which is just subtracting reposition by xi. Are there other dressing fields that are not of this form? In particular, I'm thinking about an example we had in our context where we say we cannot just move to the perspective of the ith particle, but we could also describe everything relative to the center of mass, for example. So are there other dressing fields? Or in other words, do you have a characterization of all possible dressing fields or something like this? Do you know what these are in general?
Okay, yeah, thank you for your question. I think I understand it. And yes, the point is that it's important to be able, that's why also transformation of the second kind are important, because within a certain theoretical framework, or better even model in the end, because you can develop it in abstract and then apply it to models, that you will have a way to switch among frames, to switch among degrees of freedom. And there might be cases in which you even enlarge your field space or your the model at your disposal to pick another dressing, another object as a dressing field, or just you manage maybe to build it from the degrees of freedom of our theory. And this is captured by the description. But there is not, in the same way in which there is not an algorithm to just, there are, I don't know, tools that one may use to simplify our lives in the moment in which we search for a dressing field. We know that it is characterized by some precise property. So it is addressing if it transforms in that way, it is group valued and so on. But we don't have an algorithm to say you have a theory, this degrees of freedom, you build the dressing by following. No, we have such a thing for building dressed fields, so the rule of thumb. But if you find the dressing, so to reply to your question, I think we have a way to characterize a dressing, yes, and then there are operations that one may do in the theory to find it. But we don't have an algorithmic way to find or build it. It goes case by case, and it should cover, in principle, any description from within the system, being invariant. Yeah.
So the mathematical definition is there. What do you mean by dressings? That's just a definition, but you're saying it's not like there's no algorithm or easy characterization of these maps. Okay.
Exactly. Yeah, you have to with a bundle differential geometry, with geometry in general, you can formalize it nicely. Also, for instance, for field theory in field space in bundle geometric terms, and it's very powerful and general there. But then, if you want to come to some precise model, some specific model, there you have to see which is the field theoretic content at your disposal, which are the degrees of freedom that you may use as a dressing field. So, and hopefully find it or construct it. But also there is no way, there is not an automatic way to say, okay, in this theory there is none. Because maybe you can still construct it by a combination of your degrees of freedom. So this, yeah.
Great, thank you.
Thank you.